Hey everyone, this is Anshul Sadaria, software engineer at Google. Now, in one of my previous system design videos, I talked about a very important concept of caching for horizontal scaling. In this video also, I'm going to cover one such important concept for horizontal scaling, which is sharding. But before we dive deep into the topic, don't forget to check out Scalar's free masterclasses taken by industry-leading experts only on Scalar's event page. Link is in the description below. Now, let's get sharding. Now, are you ready? I know you might be worried that I will start with a theoretical definition and bombard you with lots of technical jargon that you might not be able to understand. But let me start with a real life analogy inspired from my own experiences to explain what sharding actually is. So when I was in college, we used to have few midterm exams, we had one end term exam as well. Now the sitting arrangement of my classroom was something like this. There were 4 to 5 columns of desks. There was one table over here, and behind the table was the blackboard. Now, after the exams were over, the professor used to share our answer sheets with us to check the marks and whatnot. So in the first couple of semesters, what he did was, it was a class of 200-250 students. So what he did was, he would pile up all the papers on the table itself. Okay. And what happened was, the entire crowd of 200-250 students used to gather around the table, and it used to take a lot of time to identify their paper, check it, and then place it back on the table. Now, what happened in the next, after a couple of semesters, he changed the strategy. What he did was, instead of putting all the papers on the table, he started keeping it on the first desk of each column. So what he did was, he kept a bunch of paper from roll number 1 to 40 over here. He kept 1 to 40 over here. Then 41 to 80. Let's assume the class was 200 strength big. So 81 to 120. 121 to 160, and the last batch of 161 to 200. Now, instead of all the students gathering around the table, what they did was, they were bifurcated in different columns of the desks, and the process became so streamlined that it was very quick to check the papers and place them back. Now, this is similar to what sharding actually does. I'm not sure if this analogy was the best analogy or not, but when there are lots of concurrent requests coming to your server, it is possible that the capacity of the server is not feasible or suitable to handle that request. Okay, so let's assume that there is a server over here. Okay, let's forget the classroom example. Now, there is a server over here, and it is getting bombarded with lots of concurrent requests. Now, every server has some capacity, it has some RAM, it has some disk capacity, it has some network bandwidth as well. Okay, so these are all resource constraints, like RAM is there, disk capacity is there, and network bandwidth, and lots of other things are there. Now, these all resources are limited. So once your system or your product starts receiving more users, starts acquiring more users, the number of requests is bound to increase, and number of concurrent requests will also increase. So your server might not be able to handle such high load of request. So what we do is, instead of a single server and a single database obviously sitting behind the server, now there will be one database sitting behind the server as well. So instead of this architecture, we break the database into multiple machines or cluster of machines. Okay, now let me just get rid of our classroom example. So now, instead of one server and one database, we break the database into multiple databases. So instead of 1 DB earlier, let's say for the time being, we break it down into 4 databases. And we partition the data in the databases in such a way that no row is repeated in any of the databases. For example, if there was a row 1, let's say row 1, row 2, and row 3. Now, if row 1 lies in 1 DB, it is not going to lie in any of the other DBs. Okay, and now each of these machines in which we have partitioned our database, each of these machines is known as a shard, and this concept is known as sharding. Okay, so each of these new servers, each of these new databases, these are shards. All right. So we have understood the theoretical definition of what sharding is. Now let's move to a very naive example, and I will run through how sharding actually happens in like real systems. So this is just a hypothetical example, like there are 6 columns and this is a user table. Okay. Now I have just added a few names randomly like Anshul, John, Sam, Raj, Christina and Carol, and these are all hypothetical emails. Okay, so don't try to email me on anshul@email.com. It won't work. So in sharding, we break the database. Let's say for this particular example, I will break it into 2 shards or 2 databases. Okay. Now it depends how you want to partition the data. In my use case, what I will do is, let's say A to H. Okay. Now all the names which start between A and H, will keep them in one shard and the other names will go in the second shard. So A to H is our first shard and I to Z is our second shard. So let's see what all data is in our first shard. Now Anshul will come in first shard. So this is user ID 1. I'm not repeating the entire example, anshul@email.com and so on. But let's assume that it is going to be there. Okay. Now John will be in which database? Okay, it should be in the second database or the second shard. Now this is user ID 2. Sam will be in the second shard as well. Raj will also be in the second shard. Now these are all user IDs, just to remind you all. Okay, and Christina will come in the first shard. So the user ID is 5 and Carol should come in the second shard. So this will be user ID 6. Now we have sharded our original database into multiple shards. In this case, we are using only 2 shards. We can have 3 shards, 4 shards, depending on how much finer we want to divide or partition our database. Okay. Now hence, like since there are only 6 rows in our table, it is fine to start with an example of 2 shards. Now there is a routing server which tells the request which shard to get the response from. Okay, routing server or lookup server. So there are 2 servers sitting in front of both of these databases based on the shards. So let's say this is S1 server 1 and S2. Okay, now there will be one lookup server or master server. You can call it any name. It doesn't matter a lot for this technical explanation. So this is a lookup server. And let's say we want to add some new data. Okay, let's say there is another person with the name of Rohan, for example. Okay, so now when we want to add this particular row in the database, we will ask the lookup server, hey, my name is Rohan and my email ID is this XYZ, rohan@gmail.com, for example. Which shard should I write the data to? Okay, so Rohan request comes and there is some email ID. We don't care about it. So now the lookup server says that, hey, your name starts with R, like your name is Rohan, it starts with R. So for shard 1, your name should start with A to H, which is not in this case. For shard 2, your name starts from A to Z, which is in this case. So we will add Rohan to shard 2. Okay. And this will be user ID 7. We are just incrementally updating it. Now let's say there is a read request for from the database server. Okay. So the read request is for, let's say, Christina. Okay, so now Rohan was a write request and read request is for Christina. Now the request again asks the lookup server that, hey, I'm looking for a user with name Christina. Which shard should I fetch the data from? So the lookup server would be like that, since the name starts with C, it would be lying. Okay, it would be present in shard 1 because like the range is A to H. So it will get the data, which is user ID 5 in this case, and it will return to the user. So this is how sharding happens in real systems. I mean, this is a very naive example. The real systems, the sharding logic will be much more complicated. It won't be A to H and I to Z and such normal examples, normal approaches. So it will be much more complicated. The databases would be quite huge in the range of millions, billions, and even trillions if they are done by systems like Amazon, if it's an order table. Okay, I don't know how many orders have taken place in Amazon till now, but I would expect it to be in the range of trillions, if not zillions and so on. So this is a naive example of sharding, and I hope at this point you understood from the real life analogy as well as the actual example what sharding actually is and why do we do it. It is to increase the capacity of the system to handle more requests as your product goes further. Now it is important to understand, okay, first of all let's get rid of all of these jargon. Now it's important to understand why sharding is important, what are the advantages, and now you must be thinking that since sharding helps to improve the capacity of the server and improves the performance and all of that, all the gold is gold, but that's not the case. All the gold is not gold. Like there are some disadvantages to sharding as well, and we should keep in mind what particular use case we are having and then decide that whether sharding is feasible or not and what approach of sharding we should take. In this case, we used an approach of names, for example, the first letter of the name. We can also use the approach of user ID. Okay, let's say user ID modulo 2 in this case. Okay, since there are 2 shards. If there are 3 shards, 4 shards and so on, we could have some sort of a function wherein there would be some entity. Okay, now I forgot to explain one important part over here. Since we divided our database into multiple shards based on the column name. Okay, now this is what we use to bifurcate our data into multiple shards. This is known as shard key. Okay, this shard key is responsible for writes and reads, which shard to write in and which shard to read from. Now there could be a different approach wherein our shard key was user ID, and we could use a modulo operator or any hash function or any function whatsoever. We could just pass the shard key into the function, and based on the result we will try to write or read from the respective shard. Now as I told you, it's important to understand the advantages. Obviously, like there are a few advantages of sharding. On the other hand, all the glitters is not gold, so we will need to understand the disadvantages as well. And there are different approaches of sharding which we will cover in detail, like what all are the different types of sharding, what all are the different algorithms. So these 3 sections is going to be the limelight of this particular module, this particular tutorial, and ultimately I don't want you to be bored with all of these theoretical discussions. We are going to talk about some real systems and how sharding has worked well for them and how sharding backfired for them as well. So lastly, we will cover some case studies of real systems. I'm not going to reveal which systems we are going to cover, but yeah, hope you are hooked to it. Now let's first start with the advantages. The first advantage is obviously scalability, which we have talked a lot while I was explaining what sharding is. So as I told earlier, as let's say this is your server, okay, the original server before sharding. Now this has a RAM of 8 GB. 8 GB is quite common and normal nowadays. We have 1 TB disk capacity. And there is some network bandwidth. Now, let's say you are an upcoming startup. You start with a very simple server, a bare metal server, which is able to handle the normal capacity right now. But let's say you got some seed funding and you started acquiring more users, and your user base has grown double, triple, and possibly 10x, 100x. Okay, 100x in 1 year. So your simple server might not be able to handle such a request. So as I told you earlier, we will distribute our database. Let's say it went up till 1 billion. Okay, now your server is not able to handle that request. So we'll distribute it among a number of shards. Let's say there are 100 such shards. Okay, there are 100 such shards. Now all of them have 8 GB RAM. Okay, I don't know the actual RAM capacity, but we are taking an example. So 8 GB RAM is present with all our new shards and new servers. All of them have 1 TB disk, all of them have some network bandwidth. So we multiplied the capacity of our server. Now, since our user base has also grown by 100 times, now we are at a better position to handle the new request with the new traffic, and the system resources are also not constrained. We are able to improve the user experience, the latencies have dropped down, and our system is working fine. So scalability is one important, all the efforts which we are doing, caching, sharding and all of that, the ultimate purpose is scalability. There will be some byproducts of this, there will be some advantages, which is not the main motivation behind why we are doing caching and sharding. If you remember what concept we are trying to cover, it's horizontal scaling. Okay, so scalability comes as along with it. So these are all top techniques of horizontal scaling. So scalability is the main, motivation behind this. Now there are some other advantages to doing sharding. Okay. Now one such advantage is high availability. Now what do I mean by availability? You must have used like services like Amazon, YouTube, and so on. Like you can't live without all of these services, WhatsApp, Instagram, and all of these apps. Now, what is one thing which is common in all of these applications? They have super high availability. I don't remember a time when YouTube was down for a few hours or maybe a day. I have not heard it at all, So all of these applications boast, or they are proud about their availability, which would be in the range of 99.9999%. Which means that within a few years, they would be down for a few minutes or at max a few hours. They cannot bear downtime more than that. Okay, if you remember in one of the news when Google was down for a few hours, it incurred a cost of a few $1 billion. So now this is the risk of having a normal downtime like a few hours. Okay, so these systems need to have high availability. Now let's understand how does sharding fit into this entire picture. Okay, earlier, like if you remember, it was just a simple server, one database, and all the requests were coming to this single server. Now it can happen due to any of the reasons, okay, natural calamity, or there is a power disruption in the entire city or whatnot. Okay, I don't want to highlight what reason it is, but a server can go down. Now, if there is only a single server and the server goes down, the capacity to handle all the requests goes away. Okay, your server is down, your product stops, and you start incurring cost, which is in the range of billions of dollars if you are a big company like Amazon, YouTube, WhatsApp, Instagram, and so on. Now, what happens with sharding is that you obviously have a lot more servers now. You have a lot more databases. And an interesting part about real use cases is that these shards are geographically divided. Okay, it can be in the same location. For example, like I'm in Bangalore right now. So it is possible that for a Bangalore-based startup, all the shards might be in a single data center itself. But for such huge applications like Amazon and so on, the shards are usually divided into multiple geographies. Now, we know if there is one server and it goes down by any error, your product goes down. But now, since there are multiple servers now, okay, if one of the server goes down, let's say the server 1 went down, server 2, 3, and 4, they are still up. So for example, if there is a request, okay, if we remember the previous example of user table, so there is a request like, hey, give me all the email IDs so that I can send a newsletter to them. Okay, let's assume that the database that we were building, okay, user table, this is meant for a newsletter service. Now there might be a use case that, hey, give me all the emails so that I can send this article to all of these people. Now, if one shard is down, okay, let me just name this shards as well. Now this is shard 1, shard 2, shard 3, and shard 4. Now if one of the shards is down, what will happen? The lookup server will be like, okay, it doesn't matter. I will send my request to shard 1, it will be denied. I will send my request to shard 2, it will return me all the emails, and same for shard 3 and shard 4. Now, even though shard 1 is down, we are able to get the email IDs from the other shards and are able to send the newsletters to a few people. Obviously, 100% accuracy of the data won't be there since the server is down, but our system would still be running. Okay, the requests which are coming to shard 1 might be redirected to the other shards. Okay, and then our system is still able to cater a part of the audience or cater some part of the data to the client. So this is a very big advantage for the tech giants, for an upcoming startup which is going to face a lot more users. They are going to incur a lot more concurrent requests. So high availability is a very big plus. Now I will talk about this, like when I talk about some of the disadvantages, when I talk about some of the use cases, I will talk about why high availability is so important. But remember this, we talked about two advantages. Scalability is obviously the main motivation, but high availability is a big byproduct of this technique. Now the third advantage is improved read response time. Okay. Now, before I bombard you with some more technical jargons, let me just reiterate on our example. Our database has, let's say, 1 trillion rows inside it. Like in the database, there is a table which has 1 trillion rows. Now, this is, let's say, it's a product table or an orders table from Amazon. Okay, so this is the database, and in that there are 1 trillion rows in it. Now 1 trillion would be, billion is 10 raised to 9, so trillion would be 10 raised to 12 rows. Okay, now this is a massive database, and in order to, like, if you want to fetch the orders placed by a user, you need to go through this 10 to the power 12 entries and then return what all orders were placed by, let's say, me, Anshul. Like, I want to find out what all orders were placed by me. So I need to go through all of these entries and then return to the user. Now, fortunately for us, the system capacities are quite good. Like in SQL and NoSQL, the system capacities are good enough to handle such big traffic. But let's say we want to improvise the user experience. I am a very frustrated user. I am very impatient user, and I don't want to wait for 1 second or even a few hundred milliseconds. Okay, I want very quick results. So what the product might try to do is, it will try to shard this database into, let's say, 1000 shards, just for the calculation easiness. So each of these shards, 1000 shards, will now have 10 to the power 9, which is 1 billion entries. So all of these will have 1 billion entries each. And now let's say if this database was sharded along the user ID, okay, which means that our shard key was user ID, and hence one shard, like for example, let's say my data was in shard 1, then I know for sure that my data is not going to be in shard 2, shard 3 and shard 1000. Okay, like so on till shard 1000. So my lookup service, when I'm trying to fetch the data that, hey, give me all the orders placed by Anshul in last 1 year. Okay, we are adding a condition as well. So it knows that the data is placed only in shard 1. It doesn't need to go through 10 to the power 12 entries and find out. It can easily just ask shard 1, and on reduced database, it is able to handle my request. Now in optimized systems, 10 to the power 12, 10 to the power 9, I mean, it would be a difference of a few hundred milliseconds. But in systems which are so huge like YouTube, Amazon and so on, these are the experiences that people count for. Like, these are the experiences which makes this tech giants a tech giant. You know, now there is a possibility that, okay, some admin on the engineering side of YouTube or Amazon and all of these tech giants, they want all the order details. Okay, so instead of going through one database and trying to find out 1 trillion entries, it can send requests to these individual shards and tell each of them to return the particular entries. Okay, it can be, for example, the entry can be as simple as, give me all the orders placed by any user in last 2 weeks. Okay, because they want to do some analysis on top of it. They want to try and stop fraud. There can be a number of use cases for which this type of query might be very useful. So now, instead of going through a very big table, we can go to each of the individual tables and try to fetch those relevant entries and return to the admin. Now, all of these requests will be concurrent. First of all, like, we are trying to hit all of these shards at the same time, and all the 1000 requests to the individual shards would be like, hey, return me all the orders placed in last 2 weeks. So now each of the shard has a responsibility to go through the billion entries and fulfill the request. Compared to it, what, like, if there was a single shard, if there was a single server, it would take quite a significant time. Now, once all the requests are answered by the respective shards, this results will be combined and then sent to the engineer or sent to the admin for further analysis. Now, I know, okay, when I am saying that all the requests will be concurrent and we will try to parallelize and all of those things, it's not as simple as it appears. Okay, there is some overhead because we are trying to send 1000 requests. There will be some network overhead. There will be some other overheads which will try to increase the latency, but it's a trade-off. Okay, we are trying to reduce the size of our database. Along with it, there is some latency overload for the lookup server. There will be some network overload to try and combine all these entries as well. So we are aware, like we should be aware. All of us would not be aware about it. It's all right, but we should be aware of all of the things which are happening behind the scenes, that there are some benefits and there might be some trade-offs which we need to realize while we are designing all of these systems. So surely sharding helps you to improve the read response time, something which happened for a few seconds. Let's say, like if it was 1 trillion entries and I wanted to find out one row out of it, possibly if it is not a primary key, okay, let's say it's not a primary key, then it is going to take me some seconds, like it would be in the order of 1 second to 1 minute as well in some of the use cases if the indexing is not done properly. But now since we have sharded, we have multiple shards, multiple databases, along with we can parallelly try to find the response. So this reduces in the order of seconds to probably a few hundred milliseconds. So this is a big plus, though it would be like, hey, for a few milliseconds, it doesn't matter. But I have seen, like I have talked to some of my friends, they try to optimize, like they were trying to optimize from 400 millisecond to 300 millisecond. Okay. And reducing it just by 25%. Okay, now 400 to 300 is 25%. Just by reducing the latency by 25%, it helped them like get billions of profit, like billions of dollars of profit. It might seem crazy, but that's what the things are going on in real, like tech giants, real systems. Now, one more important advantage of sharding is improved write times or write throughput. Now, I was having this discussion with my flatmate, okay, and I was like, let's say there is a single server, okay, and there are a few hundred entries to it. Now, usually when concurrent write requests are occurring, there are two options. Either we serialize it or we don't serialize it. Now, for example, let's say it's a bank transaction where we don't want double deductions to happen, or let's say, you know, double charges to happen. We want to be very sure about the consistency of our system. For example, let's say I'm trying to do some payment through my UPI and I'm also trying to do some payment through net banking. Now, if both of them try to access the same database, it can happen that I was having 100 rupees in my balance and I tried to deduct, like I try to make a payment of 20 rupees each. And since both of them are occurring at the same time, there is a possibility that both of them read the same number, 100. Both of them try to deduct 20 rupees from it, which makes the balance 80 rupees, and then this 80 is written over 100. But even though we made two transactions, the real balance should have been 60 rupees. So in some of these use cases, this consistency is really important, and hence we would not be there would be serialized writes, which means that you cannot do two writes at the same time. So we will try to cover the use cases for both of them when the writes, concurrent write can happen on different rows. On the same row, it's not possible at all. We don't want to do concurrent writes. But on different rows, we may or may not allow depending on what the system actually is. Okay. Now let me get rid of this example. Let's first talk about serialized writes, wherein we don't allow more than one write in the entire database. Okay, now this makes an obvious sense that since all the write request, like that's, let's say this is write 1 request, once it is done we will send write 2 request and so on. Okay, now instead of having one server, if we divided our database into multiple shards and we had like 4 servers now, 4 shards, instead of one request, in the best case scenario, we could handle 4 write requests in parallel. Now, this is the use case when the writes are serialized, which means we don't allow more than one write to happen at one time. So now write 1 can happen in shard 1, write 2 can happen in shard 2, and this is for shard 3 and shard 4 and so on. In best case scenario, like based on the number of shards, we can try to parallelize the number of writes happening. Now, let's say like my friend was arguing that, hey, what if the writes are not serialized? What if we are able to, like there are 100 rows in this. Now our server is trying to make writes to each of these individual rows. Like at the same time, we can make all of these writes together, like write 1 till write 100. All of them can happen at the same time because they are not serialized. So now we need to realize one thing. Okay, there is one server which has a particular write bandwidth. Okay, if we realize what all different constraints are there, there are buses to carry these payloads. Okay, these are not the buses which go on road. There are network buses which carry the payloads for the write request. Now, as the number of write requests increases, let's say even if we have 1 billion data entries in this database, okay, we can parallelize all of them, but the bottleneck becomes our write bandwidth, the write network bandwidth. And in order to improve them, we obviously cannot cater all the 1 billion write requests at the same time, even though they are not impacting the other rows. Theoretically, we could send the parallel request to 1 billion entries, but practically the bottleneck is the write network bandwidth. So now if we try to shard our database into, let's say, 100 shards or thousands of shards and so on, which is the real capacity of how much sharding happens in this big systems, let's say even if it's like we had 100 rows, we divided into 10 shards of 10 rows each. Now, because of the constraint, because of the bottleneck of network bandwidth, we multiply our write network bandwidth by sharding. And this means that even though theoretically our initial system, our single database system was able to handle concurrent write request to all the rows at the same time, it was not able to respond to it because of the bottleneck in our write network bandwidth. But now, since that bandwidth has been multiplied, if the writes are corresponding to those individual different shards, 10 different shards, okay, write bandwidth has multiplied, and now because that bottleneck has eased down, what we were talking about, which was possible theoretically, we were saying that 100 writes can happen at the same time, which was not possible practically. Now that theoretical thing can be replicated in the practical use case as well. So this obviously happens us with better write throughput as well. Now we need to understand this is beneficial for use cases where the writes are happening in different shards. We need to shard the systems in a particular way. Now let's say, for example, if the writes were happening in one shard only, so even though we have multiplied the write network bandwidth, it's not going to give us the results, because now again all the write requests are going to the same shard. Okay, so we need to be very mindful how we are sharding our database, what logic we are using, what approach it is, okay, which we are going to talk very soon. And obviously, like, what is our shard key, what are the ranges and so on. So we talked about 4 advantages, starting with scalability, which was an obvious one. Then we talked about high availability, which is very important. And then we talked about better read response time and better write throughput. Now, I told you earlier, all the glitters is not gold. There are a lot of disadvantages as well. And let's try to cover all of them one by one. Okay. Now, before I explain what data rebalancing is, I want to explain a situation that can happen very commonly in sharding if we are not very cautious about how we have sharded our database. So if you remember the earlier example, when we sharded the user table, we had a alphabet range. So let's say now if I have an alphabet range of A to H and then I to, for example, M, N to U, and then V to Z. Okay, now these are 4 ranges in which we have sharded our database. Okay, earlier it was A to H and I to Z, but now I have just changed the ranges for each of the shards. Now, if you are aware, like Indian names usually like R, S, T, like those are the very common alphabets with which Indian names start. Obviously A, K and all of those are there. But my estimation, and I have not studied it, but let's assume hypothetically that majority of the names lie in the 3rd shard. Okay, and this can be 60%, 50%, I don't know. Hypothetically, let's assume it's 60%. A to H contains other 20%, and I to M probably other 15%, and V to Z, it's a rare name. We won't have a lot of names starting with X, Y, Z and so on. So how much is remaining? This is 80, 95 and 5% is remaining. Okay, now let's assume the previous situation where we were sending concurrent read request and write request and so on. Now, even though we have sharded the data in our shards is quite skewed. Okay, ideally we would want 25% each, but that is obviously not the correct expectation to set. It would be like all of them should somewhere be between 20 to 25%, like 20 to 30%, so that we can achieve the scalability and concurrency that we were expecting. Now, if there is highly skewed data in one shard, then the ultimate motivation of scaling our database fails, because most of the read and write requests again are going to the shard 3 only. Okay, let me just write the shard names. So most of the requests are again going to shard 3, which defies our purpose. Now in this situation, what we do data rebalancing. Okay, this is where data rebalancing comes into place. Now we can either just reshard the shard 3. Okay, we just try to, like, n to u, we can just try to increase more ranges, like it can be n to p, for example, then q to r, and s to t, and so on. I mean, I don't know, I'm just giving a hypothetical example. But one such approach can be like this. But usually when we reshard it, it's highly possible that we try to increase the ranges in other shards as well, which would mean that the data that is currently lying in the respective shards won't live at the same shard, like they would need to be replaced to some other shards. And when this migration happens, there will be some downtime. I mean, let's say shard 1 changes from A to H to something like A to K, for example. So earlier the data which was there in shard 2 needs to be moved to shard 1, and probably like all the shards will be reorganized in some way. Or let's say we changed our partition key, our shard key, from name. Okay, earlier it was name, if you remember. Now it becomes user ID. Okay, now this changes everything altogether, right? So there is no correlation between username and user ID, and it is possible that none of the data which was lying in the previous shards would be in the same shard again. Now this incurs downtime, and it obviously affects the availability of the system, right? So this is a big cost if we are not sharding the database by proper partition key, proper shard key, or proper approach. Okay, like this was a range based sharding. If we, like, this is not a very good way to shard the database, because we decided these ranges. Okay, these ranges which were decided earlier was based on what the distribution of the current data is. When your system grows, this distribution might change. We are not aware what new users will be added to our database. So it is highly possible that current situation will differ highly with the future situation, and these rebalancing will keep on happening at regular intervals. So downtime will also keep on occurring at regular intervals because of the migration, and this is one of the disadvantages in case the shards grow disproportionately. Now this affects availability. Okay, availability is affected. Now let's talk about the second disadvantage, which is costly join operations. Now, if you have taken your database classes in college, or if you have read some articles, you would know what joins are. If not, I am going to explain in brief what joins are and what databases, like why do joins are required, why are joins required. So let's say there are two tables in a database. Okay, a database can have multiple tables. So this is T1 table and this is T2 table. Now let's say there are two columns A and B in this, and in T2 there are again two columns A and C. Now in this case A is the primary key. Okay, in T1 A is primary key, and in T2 A is foreign key. Now when we want to perform a join, okay, let's say this is for example, this is user table and this is product table. Okay, and A is a user key in this case and C might be a product key or something like that. So now we want to do some sort of a join to identify what addresses, like B can be address, let's assume B is an address. Now we want to find some correlation between the products, which is C, column C, and what addresses they are delivered to, which can be column B. So in this case we will try to do a join. We will try to identify from table T1 and T2 for the same value of A, what products were delivered to what addresses. Okay, this is one such use case in which joins can happen. Now imagine a situation in which this database was sharded. Okay, now this can be considered shard 1. Okay, now a similar shard 2 will also exist. Okay, Now the same tables are there, the schema won't change. Same tables are again there in another shard T2. Okay, now it is possible that we sharded our databases based on the user key, user ID, or it can be product ID. I'm not sure. Any one of the following, it is possible that let's say our user ID 1 is in table 1, but there are a few products which are also there in shard 1. Okay, now this is shard 2. I know I have messed up the left and right. Shard 2 is on the left and shard 1 is on the right. But let's say our user 1 in table 1, which is the user table, it lies in shard 2, but there are a few products ordered by user 1 in shard 1 as well. Okay, so there might be some entries corresponding to user 1 in another shard. Okay, so in this case, if you want to perform a join, what shard 2 needs to do is it needs to fetch the data from shard 1 that, hey, give me all the entries of user 1 in table 2, and then I will combine them, and so on for all the user IDs. And the same thing shard 1 also needs to do. Let's say in shard 1 table 1 there is a user with user ID 74. Okay, just a random number. So there is possibility that there are some orders placed by user 74 in shard 2 table 2. Okay, so in this case, shard 1 also needs to fetch some data from shard 2. It will also ask the entries from table 2 that, hey, give me all the entries corresponding to user ID 74. It needs to combine all the entries, and then like shard 1 will do its computation, shard 2 will do its join, and so on. Now this is only for 2 shards. Imagine if there are 100 shards. One shard will query from 99 other shards, and all of these 100 shards will query from other 99 shards. So imagine 100 shards querying from other 99 shards. There are 9900 queries of different user IDs from each of the other shards. Now this consumes a lot of our network bandwidth, okay, because these shards are not lying in the same machine, right? They need to be fetched from other machines, so it occupies our network bandwidth, and ultimately what would happen inside one machine happens across different machines and incurs latency. Okay, there is a cost of the read response time in this case, which reduces our latency. So costly join operations is, you can say, one of the disadvantages of sharding. So if we are not careful how we are organizing our data, we can incur higher latencies for some of our use cases. So in this case, the latency takes a dive in some use cases, obviously. Right? Now moving on to the third disadvantage. What if the schema changes? Okay, now until now we are talking about that, like in the different shards the schema will remain the same. You know, in the previous example also, costly join operations, we talked that table 1, table 2, user ID, address, user ID, and product ID, the schema is same across all the shards. But now let's say the schema changes, and to take an example, like if you remember in the dating application system design video, I talked about Tinder and Bumble and how they store their data. Okay, so we can assume that the data is stored, like username is there. Okay, let's just keep it name is there, name, then bio can be added, and photos can be added for, like, I am uploading some photos, someone else is uploading other photos, and so on. So when my product is small, it is possible that I decide to keep the photos in the same table as my other user entries. Okay, now this is the user table. But once it has become a full-blown product where there are like millions of customers who are using the product, it is possible that storing the photos along with the other user information is not feasible from a technical point of view. So if you remember, like if you not watched the video, make sure you watch that video after you finish watching this video. But it is possible that we might decide to store photos in some other table. Okay, and that this can be a photo table, where we store the photos in the form of blob or some other choice. Like we talked about a lot of other options to store the photos. So this can be photo ID, this can be the bytes of the photo, and instead of photo over here, we change this to photo ID. Like there is a reference in the user table to the photo table. So since the schema has changed now, right, The requests which were coming to the earlier tables are no longer valid because we need to migrate the databases, we need to migrate the tables, and earlier, which used to be our sharding approach, might change after we have changed the schema. So this again can incur some downtime because we are changing the schema. Now, schema changes are not very frequent. Okay, these are big changes which may or may not be backward compatible. So schema changes should be avoided as much as possible, but at the cost of improving the performance, sometimes schema changes are really important. But on the other hand, it can cause side effects to a sharding approach, which might require to reshard our database. Okay, so while reshard, again the same issue which we, if you remember the first example, data rebalancing, we had to migrate the old data to new shards. So the same issue can happen with schema changes as well. So this can also affect the availability of our system. And this can be caused due to downtimes by migration. Okay, so now, until now, whatever changes are occurring as side effects of sharding, we saw a hit on our availability. In the previous example, we saw a hit on our latency. In the first example also, there was a hit on availability itself. Now, these are some changes which are visible to the user. If your system is not available, they won't be able to access it. The user knows about it, you also know about it. If the latency has increased, you know that your system is not optimized for some of the operations. The user also realizes those issues. Now, there is a very silent side effect which you might also not be aware. The user is also not aware, and at crucial times in crucial operations, you will realize that whatever you were expecting is not happening. And this can be potentially damaging. It can be a life and death as well in some use cases. Don't worry, I'm not exaggerating. I will tell you in what situations it can be life and death as well. Okay. Referential integrity is compromised. This is one side effect, possible side effect of sharding. Now, before I talk about what this disadvantage is, I want to highlight about what referential integrity is. Okay. Now, if you remember the previous example of user table and product table, I will just quickly redo it. So there is table A with columns A and B, and there is table T1 and T2, and this is column A and C. Now, A, if you remember, it was a primary key. Okay, this is a user ID, and in products table, we are using this as a foreign key. Now, for example, let's say a user wanted to deactivate their account from some service, okay, Flipkart, Amazon, anything. So if they deactivate it, their entry from table 1 will go because it's the user table, okay. Let's say the user ID was 30, okay. Now, this is removed because they wanted to deactivate it, all right. It is possible that there are some orphaned entries in table 2, which is the product table, right? Now, why I'm calling them orphaned? It's because there is no parent existing for this particular entry in the orders table. In table T2, it says that there are some entries corresponding to user ID 30. But if you check the main table where the primary key actually lies, the entry corresponding to 30 is not there. Okay, so it can cause to some misinformation when you try to fetch. For example, if you want to do some analysis, as I told earlier, okay, we want to do some join and try to identify which products are delivered to which places, and we want to do some magic on top of it by big data clustering and all of that. It is possible that whatever conclusions we are getting might not be right because they are influenced by data which should not be there. Now you would be like, this is so simple. I mean, if 30 is deleted from table 1, let's also delete it in table 2. This might sound simple if it was a single server. Now, if there are thousands of servers sharded across multiple machines, it is not so trivial. Okay. Why it's not trivial? It's because in sharded servers, most of the sharded servers and most of the SQL databases which are sharded across a cluster, referential integrity is not given. Okay, referential integrity is not guaranteed. In a single server, it can be guaranteed. Most of the SQL databases do provide that. But if the data is across shared databases, referential integrity is not guaranteed. Now, in this case, what we need to do, we need to write some code in our application server. We need to write some code on our own to try and delete all the entries from the other shards. Okay. First of all, let me make a note over here. In sharded servers, referential integrity may not be guaranteed. Referential integrity not guaranteed. Now, this leads to some changes in the application server, and this increases the operational complexity. This also increases maintenance cost because now we are responsible for that code. Earlier, SQL would be like, don't worry about it, I am maintaining the referential integrity, nothing will happen. But now the responsibility is on our hand, it's delegated to the application server, and they need to be very cautious that such changes are made as quickly as possible and they are consistent. So since I told that sharded databases don't have the luxury of referential integrity across the shared databases, this referential integrity is compromised and hence it affects the consistency. Now, in one of the real life case studies which I'm going to talk about, I'm going to tell how a hit on consistency affects the user experience. Okay, so in this case, you are not aware, right? There is no visible difference, like user doesn't know that, okay, there are some products in the product table corresponding to user ID 30. We don't know, like the engineers also don't know that such an inconsistency exists. So you might lead to some inconsistent data, inaccurate data in your analysis. So consistency is affected in this case. Now this is a silent thing, and this will not notify you. Even if you are monitoring, you might need to set up some cron job to try and identify if referential integrity is maintained over a period of time or not. So there are operational costs. Okay, let me write down what are the side effects of it as well. There is operational complexity. Okay, now there are maintenance costs as well because we are responsible for it and SQL is not. So these are the 4 disadvantages or 4 side effects of sharding which I wanted to highlight, because all the glitters is not gold. You decide that, okay, scalability is there, it's amazing, availability is there, it's amazing. But we need to be wary of what all potential side effects it can lead to. Okay, now a lot of talk about the advantages and disadvantages. Now it's time to talk about what all different types of sharding approaches are there. Okay. Now the first approach is horizontal or range-based sharding, which we have already talked about. But let me just talk about it once more in the context of what use cases it's more beneficial for and what disadvantages it can lead to. Okay. Now let's say our database, again, it was like there are 2 shards, shard 1 and shard 2. All right. Now this stores the data from A to H, and this stores the data from I to Z. Now, like we talked about the side effect of data rebalancing, which can happen, right? This is a side effect which we want to avoid as much as possible. And why this can happen is because like we are making a decision based on the current situation. Our current situation motivates our ranges, and our future scenario might not adhere to the previous ranges. So it is important to understand that we might need to rebalance it again and again, and there are incurred cost of availability. Our availability might take a hit. So now why use this? First of all, it's a very simple approach. I mean, there is no operational complexity. The application server side code is also quite straightforward. Like I shared in the example that, okay, there is some request for Rohan or Christina. We know that the lookup server doesn't need to do a lot of operations. Now, it is possible that there is some static data, okay, which doesn't change a lot in future. Let's say it's student data. Admissions are over, we have added all the students to our database, and now we don't foresee a lot of changes unless someone drops out, okay, which is also rare. But let's say we don't foresee a lot of changes in the future. Some changes might happen in the next year when a new batch comes in. So the data is not going to change, okay. It can have a lot of read request, right? Fairly possible. But in this case, our distribution, we are ensuring by some margin, we are ensuring that the distribution of the data across different shards might not change. So in the use case where there is static data, we might not need to worry about this skewedness. And obviously simple logic, very fairly straightforward, and less operational cost. I would not say no operational cost, but there is less operational cost. Okay, now we have talked about horizontal or range-based sharding. Now you might be wondering why we are calling it horizontal. I mean, is it because it's a kind of horizontal scaling approach? No, it's not. Now, up until now, we kept talking that the database schema will remain the same. Okay, we won't change it. But if you remember the example of Tinder and Bumble that I took earlier, where there is possibility of schema changes, it is possible that we might need to move to a different sharding approach. And for some use case, I am going to tell that in detail, but for such use cases, it is possible that we move on to an approach which is known as vertical sharding. Now, vertical sharding is not at all relevant to vertical scaling. Okay, this is not relevant to vertical scaling. Now, what vertical scaling would mean, we would try to increase the capacity of our single server itself. We try to increase RAM, we try to add more CPUs, GPUs, we try to increase the disk capacity, we try to add some buses for increased network bandwidth as well. We are not talking about vertical scaling over here. We are talking about horizontal scaling only, but the type of sharding is vertical. Now imagine, like, I'm assuming a lot of you would be using LinkedIn and hopefully you are following me over there. But let's talk about the LinkedIn database, okay, what it would look like. There would be a user table. Okay, let me just change the color. Now there would be a user table which stores information about what company he or she is working in, what are the experiences, what is the education, and so on. So there is user table. Now there can be a connections table which talks about that, hey, what all different connections Anshul has, or what all different connections you are having, and so on. So there is another table for connections, or you can have it in the same table, like it depends on what type of database normalizing you are using. But let's assume that there is a different connections table, and then there is a different table for the articles that we are putting up. Okay, articles are the LinkedIn posts. Okay, let me rename it to post itself so that there is no confusion. So there is a post table as well. Okay, so now it is possible that if we are storing them all on the same server, it can bloat after some time, right? Like even though we have sharded it, let's assume it's sharded, it is possible that because of the size of the post, our current architecture of keeping all the tables together in one shard might backfire, because we are aware now people have started putting photos with the LinkedIn articles. Okay, LinkedIn posts, people are putting photos as well. There is some sort of an algorithm, I don't know what it is, but I have also started doing it. Now all the influencers are also doing it. So this can cause the database to bloat even though it is sharded, and we might decide that let's not keep the photos. Like for the post table, okay, there will be some text, there will be some photos, there will be some likes, comments, and so on. Okay, everything is there. Likes are there, comments are there. I'm not sure what other thing can be there. Reposts can be there. Okay. Now this is what I think is sufficient for a post table. But because of the photo column in this, it is possible that the post table bloats, and we might move to an architecture, as we discussed in Tinder and Bumble as well. We might move the photos table outside, okay, and we might decide to store it in a different shard. Okay, we might have a different shard for user table, shard 1 for user table. We are storing different tables in different shards now. Okay, and all of them will have different schemas. Let me mind you about that. Now connections table is in shard 2, and for post we are keeping two different tables but in the same shard. Like photos can be in a different photo table, and we can refer it using a photo ID inside the post table itself. So this can be shard 3, like post table is there, and then there can be a photo table as well. Now I am really sorry for my handwriting and drawing, but it is what it is. So now this leads to a schema change. Obviously, we might need to incur some downtime as well because our features have changed people have started behaving in a different way as what it was expected when the sharding was done earlier. So now our sharding approach has changed from horizontal sharding to vertical sharding, wherein we divide different features in different shards. Now, why this approach is beneficial? It's because our user table is a more confidential or a private sort of a table. So we might have different type of policies for it. For example, the consistency policy might be different. We might want to replicate the database or replicate the table. So our replication policies might also differ. And we might not want the same policies to be in the connections shard 2 or shard 3. Okay, so based on the type of feature, we now have the luxury of having different controls over all of these features. We don't want the user table to be compromised, so each shard has the luxury of choosing their own controls and own policies. This is one big advantage of vertical sharding. Now, a very crucial disadvantage which we might forget in the hindsight is that the features are still evolving. Okay, it is possible that we might need to reshard it. We might need to horizontally reshard it or vertically reshard it. We don't know. Features are growing, and it can lead to one feature getting divided into more such features and more such vertical shards in the future. So again, like this has the same disadvantage. We might want to reshard it, which can cause to migrations, like it can lead migrations, and this can affect our downtime and hit our availability. Right? So you need to be very cautious when you are resharding it. You need to think with forward compatibility in mind, that what features we are planning to roll out in future, how is it going to affect my current sharding approach, current sharding architecture, how will be my write and read request be affected by it, and so on, and then make a call about what our shards should be and how they should be partitioned. Now, the third sharding approach. Now, these two were fairly simple, where we were dividing along the column axis or the row axis. Now, the third type of sharding is a key-based sharding, okay, or a hash-based sharding. Now, I will explain you like why we are using hash-based sharding over here. So, let me give you an example. So, earlier, if you remember, there was a table with a lot of user IDs, right? So, let us focus on the user ID being the shard key over here. So the user ID can be 1, 2, 3, 4, 5 and so on. And let's say we want to have 3 shards. Okay, let me add a row 6 as well. And let's say we want to have 3 shards now. Okay, shard 1, shard 2 and shard 3. Now, if you remember, I told something earlier, which was like whenever the data is getting entered into one of the shards, we pass it through a function. Okay, it can be a hash function or it can be some other normal function as well. We do some computations on top of it. So it is some sort of a hash function itself. Okay, so we hash our shard key, and based on the result of it, like whatever the hash is in the response, based on the response of our hash function, we will decide which shard we should write the data into and which shard the data should be read from. So now let's assume a very normal hash function, which is in this case, like we can have a modulo 3 because there are 3 shards. Okay, and shard 3 will correspond to the modulo output 0. Okay, so now the first entry, user ID 1 modulo 3 is 1, so we will keep that entry in shard 1. Now shard 2 will have entry for user ID 2. Shard 3, for shard 3, the entries 3 and 6 will go in shard 3 because 3 modulo 3 and 6 modulo 3, both of them are 0 and so on. So 1 and 4 are in shard 1, 2 and 5 are in shard 2, and 3 and 6 are in shard 3. Now let's say there is a request that, hey, can you return me the response? Like I want the email ID for the user corresponding to shard 1. So now first of all, we will do the hashing. We want the output for user ID 1. So we will follow 1 modulo 3, which is our hash function. 1 is the shard key over here. Okay, and the output in this case is 1. So now this will decide which shard the data should be fetched from. So it will tell that, hey, my output is 1, so please get the data from shard 1 and so on. And similarly for the write also, let's say there is a new entry. So it will be user ID 7. So we will try to compute in order to compute the hash for it, we will try to compute 7 modulo 3, which is going to be 1. So we will put the entry corresponding to user ID 7 in shard 1. And if it further grows, we'll put the other entries as well. Now let's say our database has bloated. Okay, now there are 10 users and we want to reshard it. If you remember in data rebalancing, we want to do it. So it is possible during peak times, like for example, Diwali is coming, so Amazon and Flipkart, they would have a lot of sales. So that traffic will increase at such times. For example, Hotstar, okay, World Cup final is there or some other occasion is there. So at that time, the traffic will increase and we want to scale our database by increasing the number of shards. So right now we have 3 shards. It is possible when we are expecting a traffic spike, we might want to increase it from 3 shards to 5 shards. Now, what happens if we increase to 5 shards, right? We need to change the hash function as well. If the hash function was the same, shard 4 and shard 5 will remain empty because there is no output, like the output of the hash function which matches to those shards. So we will change our hash function from modulo 3 to modulo 5 now, and we might need to rearrange our data. So let me just get rid of the main table and we can see how it affects our data entries. Now shard 1, shard 2, shard 3, shard 4 and shard 5. So user ID 1 and 5 or 6, yeah, 6 in this case, 6 modulo 5 is 1. So 1 and 6 will be in shard 1, 2 and 7 in shard 2, 3 and 8 in shard 3 and so on. Now the current data is differently organized than what the ideal data should be for 5 shards. So now what this will lead to, this will lead to data rebalancing. We will need to update our shards. And in this approach, when we are increasing the number of shards or decreasing the number of shards, since it is difficult to change the hash function in between, we might need to stop the system from adding, like from having new writes or from having new reads. And again, this can affect our availability. So this can also lead us to downtimes when we are migrating from one hash function to another hash function. So it can lead to downtimes when we are migrating the data, and it can affect our availability. So now, like when the traffic increases, the traffic spikes, we might want to increase the number of shards. When it decreases, we might want to decrease the number of shards. And this elastic scaling will keep on occurring, scaling out and scaling in. Okay, scaling out means increase the number of shards, scaling in means decrease the number of shards. So these might be very frequent because a lot of sales are coming on and then they are also ending after a few days. Okay, Dussehra sale can be there, Diwali can be there, Black Friday is there, Christmas is there, and so on. So it would be very impractical if we want to change the hash function and we want to incur downtimes again and again. So this is one disadvantage of hash-based sharding, and this you can overcome by using consistent hashing. Okay. Now this can be overcome using consistent hashing. I'm not going to cover consistent hashing in detail, but if you want to understand it in brief, I have talked about it in Uber's system design video earlier. So consistent hashing, we can use that to change the hash function on the flow. Now let's talk about the last type of sharding, which is directory based sharding. Okay, now this will help us to get rid of the side effect which was caused to us by hash based sharding, in which we were not able to change the number of shards, like elastic scaling was not possible on the fly. So first of all, if we are adding consistent hashing, it incurs some operational cost. Okay, it incurs some maintenance as well. So it is a costly operation, even though it helps to mitigate the issue of availability and downtime. All right. Okay, so now we are on the last type of sharding, which is directory based sharding, which helps us to mitigate the issue of elastic scaling. Okay. Now in directory based sharding, let's say we are following the same example as earlier. Let's say we have 3 shards, shard 1, shard 2 and shard 3, user 1, user 4, user 2, user 5, user 3 and user 6 in the respective shards. Now instead of computing from a hash function and deciding where the data should lie in or where the data should be fetched from, we will use a lookup table. Okay. Now the lookup table will tell you that for a shard key, what shard should the data be fetched from. Okay. So now if the shard key is 1, fetch the data from shard 1. Now it's kind of an index, you know. For example, there is a book, there is an index of what different chapters are there. So you can expect that what content would be in which chapter. So similarly here, the first thing that we'll do is we will have a lookup server with a lookup table, which will check in the table that where the data entry, like where the data should be fetched from, which shard should it lie in. Okay. Shard 2, shard 3, shard 1 and so on. Okay, like I'm assuming you will be able to understand which shard the remaining keys will lie in. So now, like we have understood what the flow is, but let's say there is a new data entry. We want to add a new user 7 to the table. So we will need to add an entry for that in our shard table or in the lookup table as well. So this is our lookup table. We will need a corresponding entry in the lookup table as well. So we'll need some sort of a function. It can be a hash function as well. So we'll need some sort of a function to decide which shard the data should lie in, but then that entry will be kept in our lookup table as well. So let's say we added 7 in S1 and so on, like our lookup table will also correspond to those changes. Now the key part over here is that how do we make into effect elastic scaling? Okay, we want to increase the number of shards from 3 to 5. So we change the hash function. How can we change it without affecting our availability? So the old lookup table remains as it is. Okay, whatever new entry comes in, okay, whatever new writes are there, they will correspond in a new lookup table and in new shards. For example, we are adding shard 4 and shard 5. Okay, let's say we are adding a user 11. So user 11, now we have a fairly new architecture, like we have a fairly new database, global database, ranging from S1 to S5 now. Now we add a new user 11. So 11 modulo 5, it should be in S1 and so on. Like we will keep populating. For 14, it will be in S4 and for 15, it will be in S5 and so on. New data goes into the new shards and we will keep populating the new lookup table. So if we want to fetch some data, we will first check into the new lookup table. If it is not there in the new lookup table, we will check in the old lookup table and fetch the data from the old shards. Now we need to migrate the old data to the new shards as well, right? So S1 from user 1 to user 10, we need to migrate them from the old shards to the new shards. So while this migration is happening, once we have migrated, let's say we migrate user 1 from the old shard 1 to the new shard 1. Okay, both of them, even though their names are same, they are different shards because they are different architectures. So when we move user 1 from shard 1, let me take a new example so that this confusion doesn't happen. Let's say 1 remains where it is. We move user 4. So it is no longer in shard 1. We move it to shard 4, which is a new architecture. So in the old lookup table, we will get rid of this entry corresponding to user 1. And in the new lookup table, we will add the entry for 4. That user 4 should lie in shard 4. Once all of these migration is over, we get rid of the old shards, we get rid of the old lookup table, and we now have a new lookup table with new architecture. In this way, same way, like if we want to scale it in as well, we want to reduce the number of shards, we can again change the hash function and use the same approach to like reshard it. This doesn't affect our availability, which used to happen in the earlier case because there was no bookkeeping possible for two different places. Okay, we don't know where the new data would lie, we don't know where the old data lies. So without a lookup table, this was difficult. But now again, all the glitters is not gold here as well. What's the issue? The issue is there is a lookup server which incurs some latency cost as well, because now we need to check in the table where the data should lie and then fetch it from there. Okay, so latency is taking a hit. And also we are taking one more hit, which is single point of failure. Now imagine what if our lookup server goes down. Lookup server goes down, you have no way to add new data to the database. We have no way to fetch the data from the shards as well. Okay, so our availability goes down in a way that it is a single point of failure. So obviously there are ways to mitigate it, single point of failure. Now for such crucial databases, for such crucial tables, we will have a master-slave architecture, wherein if the master goes down, we will make the slave a master, or if there are multiple slaves, then we can do some sort of an election to elect which slave should become the master. Okay, so now these are the different types of sharding. We talked about different advantages, we talked about different disadvantages as well. Now it's important to understand when we should actually use sharding. So now we need to understand that when we should actually use sharding, because we saw the good sides, we saw the bad sides, every coin has two sides. So when we should actually use sharding? We should use sharding when we know for sure that our single server architecture, our single database architecture is no longer able to cope up with the increasing traffic. Okay, so this is number one. When we know single database can't handle it. We also need to have an awareness of what all different features are there. We need to understand what our shard key is. Out of the 4 approaches I talked about, which approach might be best feasible for what shard key and for what use case. Okay, it is possible that we shard different features and different types and then fetch the data accordingly. So we need to be aware about that as well. Obviously, it will be adding some complexity. Adding some complexity, awareness of features, and so on. I mean, I have talked about when to use what type, what are the advantages of a particular type of sharding, what are the disadvantages, and so on. So by this time you would have a fairly good idea of what the optimal approach for sharding is and what my shard key should be. Now I promised you that we will talk about some real life case studies. So let's move on to that part. So the first case study that I want to talk about is Uber. Okay, if you have watched my earlier video on Uber system design, you would have a fairly good idea about how sharding is beneficial. For example, I am currently in Bangalore. Okay, now I want to find an Uber for me. Now I want to find the nearest cab drivers. Okay, I am at some location in Bangalore over here. I want to find some nearest cab drivers. Would it make sense for the server to check through the cab drivers who are currently in Los Angeles? No, right? I mean, that's just a waste of time. So in this case, we can shard the data in such a way that it's geographically distributed. These are known as like geo-hash based shards. Like geohashing is one way to distribute the data. So only the data which is near my current latitude and longitude, we only need to choose the nearest cab driver from that. Okay, there will be other choices like are they completing a ride, what's the end location, what's the start location, what's the driver history, and so on. But that's for some other time. I wanted to highlight over here how geo sharding is beneficial. So you must be aware that Uber keeps on adding new cities incrementally. Like when it would have started in India, it might have started with Delhi, Mumbai, Bangalore, and so on, all the cities, all the top cities, and then it would have moved to other cities like Ahmedabad, possibly Gurgaon, Pune, Hyderabad, and so on. I am not sure. But the point here is they are scaling rapidly. They are entering new cities. They are entering new territories. Okay, so it would make a lot more sense if we are storing their data based on the geography. The shards are based on the geography, and then we are fetching data from the same. It helps to improve the performance. It increases the user experience as well by reduced latencies. Okay, now this was one use case of Uber. Now talking about the second use case of Instagram, like it's fairly similar to what I talked about LinkedIn and Tinder case study earlier as well. Now when Instagram would have started, they obviously would have expectations that it would be at the stage where it is right now, but they would have started with a very simple architecture in the beginning, and when the number of users increased, they would have thought that let's shard our data by the connected graphs. What I mean by connected graphs, for example, there is Anshul. I follow some people follow me. Okay, so it forms a sort of network. So it would make a lot more sense if we would shard the database based on the user IDs and the connections. So if I have a bunch of friends, like let's say I have 5 friends only on Instagram, okay, hypothetically. So we 5 friends interact with each other a lot. So it would make a lot more sense if my connected network was in the same shard. And similarly, there would be a lot of other connected networks as well. And those connected networks should ideally be in the same shard itself. So for example, if I'm commenting on my friend's photo, then he or she, they are lying in the same shard as mine. So consistency or the referential integrity which I was talking about, consistency doesn't take a big hit. Okay, so this becomes a good idea. Like we can use user ID as our shard key, and it also helps us with consistency because my connections are in the same shard and so on. So when Instagram grows, like I don't know, there might be 1 billion users using Instagram right now. It might increase to 2 billion users and so on. So now for this case study of Instagram, we saw how clusters, like sharding by clusters, is helpful based on our connections and user ID. So in case if the traffic goes, like increases from 1 billion to 2 billion as well, right, the same approach might be beneficial. Again, like they would not have to reshard it, they would not need to change their approach, and it helps to improve their performance and also consistency and all of those other factors. So latency is intact because we are sharding, like the data is distributed. Consistency is there and availability is also there. I mean, if one of the shard goes down, then it is possible because of the replicates. There will be master slave architecture for such crucial databases that the slave server can come up and handle the traffic in case the master server goes down. Now the third case study is interesting. Right now I have talked about 2 case studies in which sharding has proved to be beneficial. Now the third case study is of Reddit, right, where people post thoughts and some people comment on those thoughts and so on. Now what happened in Reddit was they decided to shard the data based on user ID. Okay, similar to what Instagram did. Right, shard key is user ID. But now as a consequence of this, like different users are in different shards. So now when one user comments on a post of another user, now in Reddit there is not such strong concept of followers or following and so on. Okay, you don't just interact with your own friends, you will comment on any XYZ person's posts or their content. So what this approach led to was some inconsistencies and frustration among the user. Let's say I am, okay, Anshul, and there is another person, Raj, who has posted something. Now Anshul comments something on Raj's post. Now, since it is possible that both the users are in different shards, the consistency is eventual consistency and it might not take into effect as we have expected. So you are expecting that your comment should show up to Raj at that same time, but it might not happen so. So consistency took a hit because of this approach, because they didn't realize the side effects of their approach, like shard key as user ID. They did not realize this side effect of consistency. Okay, so consistency took a hit and people were getting frustrated that I'm not able to see the comments, I'm not able to see the likes, the interaction is not getting propagated from one user to other user and so on. And this led to a decline in the number of users, and they had to rethink their strategy that, okay, it is improving the scalability. Scalability is a big plus, but I talked about referential integrity, like it can get compromised as well. It can lead to some data inconsistencies as well. So in the case of Reddit, whatever sharding approach they took, or whatever suggestion they went ahead with, it backfired with data inconsistencies and the number of users decreased, though at the cost of performance. But it is important to understand that performance doesn't just mean latency. Okay, performance doesn't just mean concurrent read responses and write throughput. It also means data consistency. So this is what got affected in Reddit by their choice. So now that's it with this concept of horizontal scaling, which is sharding. We talked about different advantages, we talked about disadvantages, we talked in detail about what different types of sharding approaches are there. And lastly, we also discussed 3 case studies where sharding proved to be beneficial and where sharding backfired. Now, if you liked this video, make sure that you hit the like button. And if you want to keep following such interesting content, make sure you subscribe to Scalar's YouTube channel and don't forget to hit the bell icon. See you in the next video.